Alright, so this is the makeup lecture because we lost one lecture because of the second or exam 1 pi took up one lecture. So I'm making up that lecture by recording this, and this is going to be important because your homework assignment, there will be one homework assignment to convert a Boolean expression. I wouldn't say one, there are a few, but there are a few Boolean expressions that you need to convert into CNF, into a conjunctive normal form. So section 5.2 has been expanded. It's a little bit longer than before, and that's because I really want to convince everybody that um, any Boolean expression can be converted into a conjunctive normal form. So that's what the first portion of it is about. Okay, so if you read this part here, that's all new, and basically it is theoretically explaining why a general Boolean expression can be turned into a conjunctive normal form. So I'm going to start with this first, because I think it's important to understand why theoretically this is doable. So we are going to start with this statement here. This is because any Boolean expression involving n variables can be represented by a truth table that has 2 to the power of n rows. There are n plus 1 columns, n of them corresponding to the n variables, and the extra one corresponding to the value of the expression based on the values of variables on that row. Alright, so we'll go ahead and digest this particular paragraph by using an example. So let's see. I'm going to use my local spreadsheet, just because it's faster and more efficient this way. All right. So we'll also basically use a somewhat familiar example, which is the one that we talked about before. And this time we'll have one, two. Yeah, I will have just two. So we'll have two expressions and three variables in this case. All right, so we'll start with the variables. We have variable p, variable q, and variable r. And the way we derive a truth table, is to first assign values to these variables. Now, if there are three variables, then we have 8 rows. Now, why do we have 8 rows? That's because when p is true and when p is false, q can be true or false. True or false. Now, when both p and q are true, r can be true or false. When p is true, q is false, r can be true or false. So you can see why there's a very specific pattern to generate the values of p, q, and r. So the next thing we're going to do is to evaluate a certain Boolean expression. Okay, so we are going to express p implies q and q implies r. So there we go. So now you might say, oh man, this is going to be a chore to do everything by hand. The answer is yes, it is kind of a chore to do everything by hand. There's a little shortcut to get this done kind of more quickly, and that has to do with using formulae in the spreadsheet. So I'm not going to do that. I'm not going to cheat. So we are going to do this by hand, okay, the long way. So p implies q and q implies r is true in this case. P implies q is true. Q implies r is false, so the conjunction is false. P implies q itself is false, and therefore the conjunction is false. And same reason why this one is false. This one is true because P implies Q is true and Q implies R is also true. So when I look at this, I'm doing a lot of mental, quote unquote, math or mental logic because I'll just use this as a very specific example. So for this particular row, P has a value of 0, Q has a value of 1, and R has a value of 1 as well. So if p has a value of 0 and q has a value of 1, 0 implies 1 is indeed true. And then we have q having a value of 1 and r having a value of 1 as well. True implies true is also true. So then we have true and true, and as a result, we put an entry of true over here. This one is false because q implies r is false in this case, and when you have at least one component being false in a conjunction, the entire conjunction is false. This one is true, and this one is true as well. Okay. So this is what I mean when I say, any general expression, Boolean expression like this one, can be represented by a truth table. The size of the truth table is limited only by the number of variables. Now, if I add one more variable, like variable s here, then we're going to end up with 16 rows, not 9, but 16, because the pattern of PQR is going to have to be repeated, over here, and then we will have one block of these corresponding to the new variable s being true, and then the entire other block corresponding to when the value of s being false. So every time you add a new variable, the size of the truth table is going to double. So that means if you have just 8 Boolean variables, you're going to be dealing with a table that has 256 rows. And if you have 16 variables, then your table is going to be 65,536 rows long. So yes, it is an exponential kind of relationship, but we are not concerned about how it scales, or in this case, it doesn't really scale very well, but we are talking about it is still finite, okay? All right, so now that we know this, what are we going to do to show that CNF is indeed complete when it comes to expressing a Boolean expression? So we're going to put this one to the side first, and it will show a few terms here. All right, so the next one starts with any additional term to a conjunction further restricts the value of the original conjunction. So that's awfully vague in terms of what it is trying to express. So what I'm doing here is to say, okay, let's just consider P and Q as two Boolean expressions. And one of these two can be a conjunction, right? So P can be the conjunction and Q is an additional term that we want to AND to the original conjunction by therefore extending the length of the conjunction or adding more terms to the conjunction. So the term to say this in a very concise way, we are basically saying P and Q implies P, and likewise P and Q implies Q are always true. So does that make sense to you, right? So if you do not have an AND Q here, P implies Q is always true, and that's always true, right? Because if P is false, then we have false implies false, and then the implication is true. If P itself is true, then we have P implies P, which is 1 implies 1, or true implies true, and in that case, the implication is also true as well. So when you have the conjunction with Q, I mean, this term here can only turn from what was originally true to false, potentially, right? It depends on what Q is, but it cannot turn something from false to true. And therefore, it is not possible for this implication to be false, and it is not possible for this implication to be false. Okay, and the next sentence is simply saying, okay, how do we interpret this, right? So the way to interpret it is impossible for P and Q to be true, but P itself is false, and it is also impossible for P and Q to be true, but Q itself is false. So what is the bottom line of this paragraph? I mean, this is fairly evident, that's one of the properties of conjunction, right? Because you need both sides of the conjunction to be true in order for the result to be true. So what this is trying to say is if you start with a CNF and you add one more DE or disjunction term to the original CNF, you can only be restricting how many rows. Now that becomes important to show this table here. Then it becomes important to understand that when you add more terms, you're basically turning more of the rows into zeros. Now let me show you why what that means. Okay, so we are gonna cut and paste this one to this column here, and then we'll go ahead and just have P implies Q over here, and we'll have Q implies R over here. So I'm gonna populate the table really quickly. So this is true, this is true, this is false, this is false, this is true, 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 true. Okay. Now, if you're wondering, what do you mean by these true and false values, you might need to revisit the truth table of implication. And I'm just going to say that much and leave it at that. Okay, if you're still convinced, you're not convinced why I can compute column D this way, go ahead and ping me on Discord, and I'll be more than happy to explain to you. All right, so we'll now work with Q implies R. That is true, false, true, 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 false, true, true. Okay, there we go. So now we take a look at the original term, like this one. We have, true, true, false, false, true, 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 true. So when we add a new term by making a conjunction with Q implies R, so we'll just go ahead. Okay, let me do this. Okay, I'm going to do this, and then I'm going to do that. There we go. So we are only comparing the highlighted cells. So P implies Q itself is true more often compared to P implies Q and Q implies R. So there are certain rows here, which is like this row here. Okay, it was actually true with P implies Q, but when we have a conjunction, it is now false because because Q implies R is false for that particular row. Another example is going to be this one, right? Because P implies Q is true, but because Q implies R is false, then the conjunction of the two is also false. So that means as you add more terms to a conjunction, as you're anding more terms, you're basically turning more values of the expression to be false. Is that okay? Well, obviously, I cannot hear you because I cannot time travel into the future and figure out whether you have a question or not. So that's kind of the downside of asynchronous lectures or the flipped classroom. Anyway, we're moving on. Okay, so when we move on, we are now going back to the notes here. So I, this way, this is this portion here. Okay, let me highlight which portion we are talking about here. So this portion here is basically just arguing and say there is a way to kind of specifically turn certain rows off. Okay, and let me explain what that means. So when you have a truth table like the one that we have here, and you say, okay, so this one is false, right? So how do we specify a very specific expression to make one specific row, which is this one, to be false? So what you need to think about is we're going to use a conjunction based on these three values. So P has to be true, Q has to be true, and R has to be true. And then we use a conjunction to and P, Q, and not R in this case. So let me just write it down here so that we can see what I mean by that. So now we say, okay, so the conjunction is P and Q and not R. So you look at this conjunction here and go like, but Tach, that's not going to help us because this conjunction is true for this specific row, and yet our objective is to make it false. So it's not going to work. Then I'm going to say, well, that's a very easy way to make this statement or make this expression that is very specifically true, but only for this row, to be false and only for this row. All we have to do is to negate it first. Does that make sense, right? So if you express, okay, so I'm gonna do a cut and paste here. And if you evaluate this new expression, which is the negation of P and Q and not R for every single row, I am not going to do that myself because that's just going to be a whole lot of chore. But I will try to convince you that this is going to be the table you end up with. Now, if you are not convinced, okay, if you're going like, I'm not sure about that tag, then you go ahead and check it, right? You go ahead and evaluate this very expression for the first row. P, Q, and R are all true, okay? So if P, Q, and R are all true, then not R is going to be false. And since not R is part of a conjunction, the conjunction is going to be false. Not false is true. So that's how we can confirm one row having the correct value. So if you're not convinced, you can do it to all of the rows here just to convince yourself that this expression is going to turn exactly one row, the one that we are targeting, to be false. So now we can specify another one, right? Let's pick this one here. Okay, so this one has P being false, Q being true, and R being false. Okay, so what we want to do is to make something like that, right? It's a NAND expression starting with a not, and then we are doing a bunch of ands in between and inside the parentheses. So in this case, we want P to be negated. We want Q to be non-negated, and we also want R to be negated. All right, so I'm gonna space this out a little bit. And once again, me being lazy as I am, I'm just gonna say this is gonna be these are the values for this specific expression. Okay, and it's going to be your job and your kind of work in order to verify that these values are indeed correct for this very specific expression. All right, so where are we going here, right? So where I'm going here is to, okay, now we're going to have to move this entire spreadsheet in because the next expression is going to be pretty long. All right, but before we go there, okay, we're going to apply De Morgan's law. So when we apply De Morgan's law to this, because we can apply De Morgan's law in this case because it is a negation of and, right? So that's how we can apply De Morgan's law. So once we apply De Morgan's law, this becomes the negation of each individual item. So P was not negated, now it is negated. And then we are connecting all of those terms using an OR because that's how De Morgan's law work. So the next one is going to be not Q, and then the last one is supposedly not R, but since not R is just R, so we just say that. And then this one is once you apply De Morgan's law, then we have not P, which is just P, or not Q, or not R, which is just R. So if you're not convinced, okay, once again, I'm doing some claims here, but if you're not convinced that these are this here is the De Morgan's law. They're the same expression. They express the same thing. They are just different ways of expressing the same thing. So if you're not convinced, then what you want to do is to look at the first expression on row 1 and then evaluate that very specific expression for every single row based on the values of P, Q, and R, and convince yourself that this is actually correct. Okay, but I'm not gonna do that. Okay, that's gonna be your exercise, not mine. All right, so now what we're gonna do is we're gonna have a conjunction of these two, right? So we'll go ahead and copy and paste. Okay, so we copy and paste this one over here. And then we're gonna copy this, and this time I have to be more careful because I want to say this thing and that thing. There we go. All right, so what is the big deal here, right? So based on the early observation that when you add more terms to a conjunction, you're going to turn more rows off, right? So now we look at the first row and go like, okay, they're both ones, so the conjunction is going to be a 1. And at least one column has a 0, so this is going to be a 0. Both columns are 1, both columns are 1, both columns are 1. At least one column is a 0, put a 0 here, and so on. So you can kind of see where I'm going, right? Because now, when you look at these values, and you compare those to these values, you can see we're getting closer, right? So there are still a few rows that we haven't really converted yet, like this one and this one here. But you can see that if I just have two more terms, one term to address this one here and one term to address this term here, then I can make a CNF that expresses exactly the same truth table um, as the original what Boolean expression. That's right. Okay. But this is an easy one, okay? If you have to convert something into a CNF, this is a easy peasy one, okay? But I'm illustrating the concept here, okay? So the concept is CNF has the same expressive power as any Boolean expression. You give me any Boolean expression, I can always turn it into a CNF. It just looks very differently, but it can express exactly the same thing. All right. So there is that, okay? And when you see all these big V and a big wedge, notation, they're basically trying to express what I am showing you as an example over here, except it's much more generalized and abstracted. So that's what math does, okay? Math is a language. It is a language that takes something that is concrete like this into something that is much more generalized. But in order to make things generalized, you will need to rely on variables, you need to rely on symbols and so on and so forth, and that's why, that's what abstraction does. So, and I believe that I need to refresh this because I think I made a mistake earlier that is now corrected. Or maybe I have not fixed it yet. No, it is fixed. I'm looking at this particular expression here. It should be negated. Alright, so I'm hoping that you guys are more or less convinced that CNF is as expressive as any Boolean expressions, or we can take any Boolean expression and turn it into CNF. The question is, how do we do that, right? So how do we do that? Well, we can use Boolean algebra. And you might say, but we can also use the technique that I just show here, right? Because we can just attack or turn these rows into a false one by one. That approach is kind of tedious, right? Especially when you have a lot of variables. So if you have 5 variables, you have 32 rows to begin with. And it depends on how many of those rows are supposed to be 0 or false. If the number of those rows to be false is high, then you can potentially end up with a pretty long and tedious process to do that. But it's possible. You can actually do it that way. But it's much more common that people do it using Boolean algebra. And to do it using Boolean algebra, we have certain tricks to do those things. So I'm going to show you, instead of just kind of talk about this, which is more or less abstract, we'll go ahead and take a look at a concrete example, like this one here. So this is a concrete example. We have not P or, and then in parentheses, not, and then R implies Q as one term, and. So this negation applies to just R implies Q, and then we have a conjunction here with P or T. Alright, so the question is, how do we turn this into a CNF? So if the outermost operation is an OR, there's not much you can do about it. Okay, you basically have to wait until everything else is done before you can determine what to do with this OR. So now we say, okay, since we can't really do much about this OR, let's focus on one of the nested expressions, which in this case is the negation of R implies Q and P or T. So I personally like to get rid of implications first, because implications can be converted into the negation of the first or the left hand side or the right hand side. So in this case, R implies Q becomes not R or Q, and that's how I converted from the first row to the second row. So once you have that, whenever you see an opportunity to apply De Morgan's law, it's always good to apply De Morgan's law, because in the CNF, negation can only apply to a variable. So that means if you have a negation applied to an or when you have a negation applied to an and, you always want to move that negation in into the terms that are in the originally negated expression. So that's what I'm doing here. I'm applying De Morgan's law because we have an or here and it is negated. So we apply De Morgan's law, which basically quote unquote distributes negation into the individual term of the or, and then we turn the or into an and. So now we end up with not R and not Q. So now we do a simplification. It's really important that you do simplification whenever possible, because if you don't, you can end up with like super duper long expressions, and then it becomes very hard to handle manually. So I applied simplification so that we end up with not R becomes just R itself. So now we have an and. So in this case, I use a distribution. Um, so I use a distribution where P or T is distributed to R and not Q. So now it becomes R and not Q and P, or R and not Q and T. So I'm distributing this term over, I'm looking at R and not Q as a term, so we can always do distribution like that. And now we end up with this term, which is a conjunction or another conjunction. There's not much you can do about that either. Okay, the only way you can work with this is to expand it. So when I say expand it, it simply means using basically FOIL in this case, except this is a three-way FOIL. So now we have R and R or R, and R or not Q. So basically, I'm pairing up this R and using this operator with every single one on the other side. So that's why we end up with R or R, R or not Q, and then we have R or T. And then all of those terms are ended together because that's how distribution works. And then we take the next term, which is not Q, and then we do the same thing. So now we have not Q or R, not Q or not Q, or not Q or T. So those would be the next three terms like this. And then we take the P term and we do the same thing. Okay, so it's really boring, what we're doing here. And for those of you who are thinking, but I have no idea what distribution means in this case, there is a page that I linked to because I don't really feel like copying and pasting everything into my notes here. So if you just kind of open this page, it will show you all the laws of Boolean algebra. And it's the interesting thing is, they also actually show you the circuit, equivalence of those Boolean algebra terms, which I think is kind of refreshing. And for those of you who are more tactile, like you understand electricity and switches and stuff like that, this representation is kind of funky, but it does work. Okay. So basically, we just end up with a bunch of Boolean algebra rules, and absorbative is basically the opposite of a distribution. Well, yeah, it's kind of like that, but not exactly the same. Associative is just for kind of pairing the parentheses in a different way, and then we have let's see, where is distribution? Distribution should always be somewhere here. There we go. So we have distributive law, which turns A or B and A or C into A and A, or A and C, or A and B, or B and C. But there's another distribution. So this is another distributive law. It's the same. Alright, so I'm trying to make sure that the distributive law is explained here. Yeah, it even has De Morgan's law, but you can see how De Morgan's law actually does not have a circuit equivalence. There we go. Okay. So there are two distributive law here. So in normal algebra, there's only one, but in Boolean algebra, there are two. So A and B or C is the same thing as A and B or A and C. A or B and C is the same thing as A or B and A or C. Now, how does that get into this mess that we end up with, right? So right here. Well, it's basically repeatedly applying the distributive law. So basically, the idea is the term b here doesn't have to be a single term, doesn't have to be a single variable. B itself can also be a disjunction. So that means you now can apply another distributive. You can distribute again here because b it's by itself is. Oh, excuse me. I clicked on the wrong thing. So if b itself is a or, that means you can now apply the same law again with a and b because b is itself a disjunction. So that's nested application. So basically, you just have to apply the distributive law several times. I mean, that's basically what FOIL is, right? Because FOIL is basically distribution twice. Um, and that's what it is. So if you can apply distribution twice in normal algebra and end up with FOIL, you can probably know, okay, what if we have a plus b plus c times x plus y plus z. Well, I mean it's FOIL, but now you end up with 9 terms, right? Because each term of the left hand side pairs up with each term on the right hand side, and you end up with 9 terms. So that's exactly what I did over here. All right, so moving on. So this is a big huge mess already. Okay, so the smaller mess is from doing this, and then we have a not p or a bunch of ands, right? So it is also we can just we can do distribution again. So that way I'm distributing the not p to every single term here in the big huge conjunction. So now we end up with this gigantic term here. So this is where I broke my own rule because I did not apply simplification whenever I can, because R or R is just R, okay, and then we have not Q or not Q. That's just not Q. So I could have applied some simplifications here, but I did not. So after I expand everything, then we end up with 9 terms, and each term has each disjunctive term has 3 variables. Now, if your objective is just to convert it into a CNF, we have a CNF here. Okay, this is a CNF because if you look at this particular line here, I cannot highlight it, but if you look at this line here, we have a gigantic conjunction, and then each term in the conjunction by itself is a disjunction of either a variable or the negation of a variable. So it does meet all the requirements of a CNF already. But using this one, is, I mean, it's equivalent to the next line, but it obviously the next line is going to be a lot more simplified. So I'm going to show you how to do the simplification here. So the first simplification is whenever you have R or R, it is just R by itself. Okay, that one we talked about already. Whenever you see not Q or not Q, it is just not Q by itself. So the it shouldn't be mysterious, but this all the truths. How do we get all the truths, right? So the truths are coming from here. We have not P or P, that is true. So it doesn't matter what else we are ORing. Just having not P or P gives us this true. We have not P or P again, that's this true, and then we have not P or P, which is this true over here. And some of you are counting, and you're saying, but Tech, you're missing something here. Because what about this term here? What about this not P or not Q or T? Where is it? And this term here, this term we simplified, but where's this term here? That is also a form of simplification. So as it turns out, if you have one term like this already, not P or not Q, you can have some other terms that are ORing, not P or not Q with more things, in the OR. It doesn't matter because these two are ANDed together. So when everything is ANDed together, only the more restrictive one is really effective. The one that is more general, the one that is true more often, is useless basically. So that's how I simplify this term out of existence. All right, so we get rid of all the truths, and then it turns into something a lot smaller. So the question is, how did I turn it into something that's that much smaller? Well, it's simplification again. So you can see how we have not P or R over here, and this has the same thing, not P or R, except it is ORing also with not Q. And by applying the simplification that I just mentioned, which is basically saying if you have two terms, one is more general than the other ones, you can basically toss away the more general ones. This is the one that is more general. And the same thing applies to this one here, because not P or R or T has not P or R in it. It's just ORing one additional item. But since everything is connected by conjunction, so you can toss the one that is more general, because the more specific one is going to cause more zeros in the truth table, and there's no way you can turn a 0 that was caused by a more restrictive term back into a 1 by ANDing with something, because AND can only turn more and more entries into false, into zeros. It can never turn something that is already a 0 into true. So that's how the simplification works. And then the same thing over here, since we already have not P or not Q, so not P or not Q, which is the same as this one here, and then ORing one additional item, that's useless. Okay, that this particular term is now useless, and that's why I can keep just not P or not Q. So that's why this is the final form, and it is a CNF. Okay, so that's kind of generally how we convert a general Boolean expression into CNF. So do we have any kind of guideline of how to do this? Well, sort of. Okay, sort of. This is a little bit hard to read, and some people can basically say, okay, this is not going to help. I'm just going to do the algebra myself. That's fine. Okay. So the question is, what do we do when we see a general Boolean expression, and then what are we going to do about it? So there are this part here and this part here are trying to express the same thing, just represented a little bit differently. If you see something that is a expression or another expression, then you have a specific case. So the specific case is if phi is already a well-formed formula, and psi is also a well-formed formula, then the OR between those two is also well-formed. Now remember, in this limited context, well-formed means it is a DE or a disjunction element, or disjunction, yeah, it's a disjunction element. If you see an expression that is a conjunction, or the topmost operator is a conjunction, then you have you basically separate the two. So phi becomes its own term, because it is you want to convert phi in this case into a disjunctive element, and you want to convert psi into its own disjunctive element. So it becomes you're basically breaking it up into two different expressions to reapply these rules, and do it recursively. Now, if you see a OR and one side of it has a conjunction, then you always have to apply distribution. There's no way around this one. You always have to apply distribution to kind of turn something like this into something or something and something or something, and then you recursively apply these rules, so that in this case, after the distribution, you're going to end up with phi or rho and psi or rho. So phi and rho, you're going to basically apply this rule here, and then the other one, no, I take it back. So you end up with phi or row and psi or row. So you're going to reapply this rule because one is because the result of applying distribution is going to be an and as the overall operation. So that falls into this category here, and then you then take a look at phi or row and check whether it fits this pattern or not. And then you do the same thing with psi or row, fit it into this rule here and see if this rule applies, or which part of this rule applies. Because if phi and psi are already well formed, meaning they're both in DEs, then you can just say that the or between the two DEs is also a DE. Whenever you see a negation of an or, there's no choice. You have to apply De Morgan's law. And then whatever is the result of that, you basically put it back into these rules and go one by one and see what you can do about it. So I can tell you what's going to happen in this case, because if you apply the first rule of De Morgan's law, you're going to end up with not phi and not psi. So it's going to fit into this pattern here. So that way, not phi becomes its own thing that you have to handle, and then not psi becomes its own thing that you have to handle, because the conjunction is basically gone, because this expression turns into two different elements. It turns into two well-formed formulae, two individual well-formed formulae, and each one we want to turn it into a DE, a disjunctive term, a disjunctive element. What about the second one, right? The second one is when we have a negation on top of a conjunction. So after you apply De Morgan's law, this one turns into not phi or not psi. So it's going to fit into the pattern of the first one, but then you have a negation of something and you have a negation of something. So you'll have to look into not phi itself and see if you can apply De Morgan's law again to not phi, and then you have to look into not psi and see if you can apply De Morgan's law to not psi, and then once those two terms become clear, then you can see whether phi is well, in this case it's not phi, but you can see whether that in return is already a disjunctive element, and also check out whether not psi is also a disjunctive element. If so, then you can just say, okay, the concatenation of those two is also a disjunctive element. Otherwise, you apply the rest of the rules. So these are just kind of general guidelines. It's not you really kind of have to do this like normal algebra, with a goal that you want to turn everything into a CNF. Basically a bunch of ORs of variables and negated variables, and then all of those disjunctive elements are going to be ANDed together. So it's going to take you a little bit of time to kind of practice this, and that's why the homework or the assignment that I will assign on Monday, not now, is going to be assigned on Monday. It's going to have a due date of a week, so that should be plenty of time. As long as people get started early. But for people who wait until the last minute, that can be a crunch at the end. All right, I'm looking at the time, and we still got quite a few minutes to go. All right, so what's going to happen once we have CNFs? Then we're going to use proof by contradiction. All right, so I'm going to go forward. I'm not really sure that I should continue going forward. And the reason why I'm not sure is it's going to take a while for you guys to kind of absorb what I'm saying here. So proof by contradiction, we have already introduced the concept. Last time I used socks in a drawer as an example of proof by contradiction. So what I'm going to do now is to actually move on and talk about how we can use proof by contradiction to prove the pigeonhole principle. So we'll start with understanding what is the pigeonhole principle. This is basically the pigeonhole principle. it states that if you have n pigeons and m pigeonholes, and you have more pigeons than there are pigeonholes, then at least one pigeonhole has more than one pigeons once the pigeons all return to their homes. So that's really intuitive. Okay, if I give you a concrete example, you go like, okay, so what is the problem here, right? So let's just say that we have 7 pigeons and there are 5 pigeonholes, and now the pigeons are all coming home. It's getting dark, and we can guarantee that at least one of the 5 pigeonholes is going to have two pigeons because there are more pigeons than there are pigeonholes. So that sounds really, really intuitive. And then I'm going to ask you to prove it. Right? It is so intuitive. It doesn't need to be proven. Well, there are a lot of stories, that I can tell you. That type of thinking can get into serious problems. Okay? Yeah, just because it's intuitive does not mean that it doesn't need to be proven. Okay? Now, since I do have time, okay, I'm gonna use this kind of personal experience as a filler. When I was in graduate school, at the I would say at the early stage of my dissertation, but it really is not. Okay, but I'm gonna say it is. So at the early stage of my dissertation, my advisor, told me, okay, there's this theorem, so you can use this theorem as the basis of your dissertation, and just kind of move forward. I look at the theorem, I go like, yeah, it sort of makes sense. I can come up with lots of examples to confirm that theorem. But you can never really confirm the theorem is always true just because you can find certain examples to show that the theorem is true. So after a week, I thought, hold on a second here. It doesn't feel quite right. Okay, so I went back to my advisor and told him, about my quote unquote gut feeling, and go like, I don't feel this is necessarily true. This is not necessarily a theorem, even though I find plenty of examples to make it true. And then my advisor said, okay, if you are so strict about proving something, you can go back to this master's thesis where the theorem was proven. So I dug it up. I dug up the master's thesis, which according to my advisor has a proof of that particular theorem. So I flipped to the page, and sure enough, there was no proof. So instead of a mathematical proof, like what you guys have seen in this class time and again, it just states obviously blah 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 is true. That is not a proof. So I looked at that and go like, that doesn't convince me. So I spent a week to come up with a counter example, and I did. Okay, I actually came up with a counter example to show the theorem is not true. So I took the counter example to my advisor and say, I think unless I have made a mistake. Okay, I think this is a counter example to show the theorem is not true. Because to prove a theorem is not true, you need just one, counter example. So my advisor looked at it and was completely silent. And then finally he said one word. No, it's not what you think it is. It's a little bit more gentle. It is just oops. Okay? Or oh. Well, the story probably should have ended at that point, right? Because I have made my point. So, but no, it's not. That's not the end of the story yet. So after that meeting with my advisor, I went back to the lab and I told my lab mate, who was a master's student, basically working on about the same thing, except it's not as involved. Um, and I told him about that theorem. That's turned out not to be a theorem. It's actually not true. And my lab mate just exploded because he was a master's he was a master student, and he was almost done, and his entire work was based on that theorem. And now that the theorem is not true, I did not find out. Okay, I did not ask him. So how is that going to impact your master's thesis? The last thing that I heard him saying was, I'm gonna kill blah blah blah, name of my advisor. Obviously, he didn't quite do that, but he was really, really, really upset. So, long story short, just because something is intuitive, it seems like, this seems, it seems right. I mean, I cannot come up with a counter example yet, okay? Doesn't mean it's always true, okay? So keep that in mind, especially for those of you who want to go to graduate school in computer science or math. You really cannot be sloppy about this sort of thing. I am sloppy with a lot of things, but not something like that, okay? All right, so with that kind of story, filling in 5 minutes of our time, now we can go ahead and try to prove this. So we're going to apply a proof by contradiction. Now, whenever you want to apply proof by contradiction, the first thing you need to do is to identify what theorem am I trying to prove right, okay? So you find that theorem and then you negate it. So in this case, with the original description of the pigeonhole principle, not the entire thing is the theorem, okay? This part here, the pigeonhole principle states that given n pigeons and m holes and that m is greater than n is greater than m, this portion here, that is not the theorem. This is the basis. This is basically what we know as iota. Okay, this is what is given to be true. Don't ask me there are more pigeons than there are pigeonholes. You are given this specific condition. But because of this condition, we are drawing a conclusion. So the conclusion that we are drawing, which is this portion here, that is the theorem. This is the theorem that we are trying to prove in this exercise. Okay, so the theorem that we're trying to prove is at least one pigeonhole has more than one pigeons. Okay, that is what we are trying to prove. So that's the part that we have to negate first. So when you say, okay, how do we negate at least one pigeonhole has more than one pigeons? Well, let's think about it. Okay, so if you say at least one pigeonhole has more than one pigeons and you want to negate it, but after the negation, it means every single pigeonhole has at the most one pigeon. Let me say that one more time. The negation of at least one pigeonhole has more than one pigeons. The negation of that is all pigeonholes have at the most one pigeon. So you kind of have to first convince yourself that first, okay? But it's nothing new to us, okay? That really is nothing new. Because when we talked about quantifiers, we also talked a little bit about how we can, if you negate a quantified expression, you can do it by changing the quantifier from universal to existential or from existential to universal, and then you negate the predicate that was in the original negated quantified expression. So we are basically just applying that. Let me see if I can illustrate it with a terminal. I mean a text editor. Yep, there we go. Alright, so we can do that. I'm just gonna hide some stuff that is non-related to this class. So and then I'll show it here. Alright, so the original negation thing is, if you say it is not the case that for all x, p of x, this really means exactly the same thing as there exists an x such that p of x is false, or you can just say not p of x. They mean exactly the same thing. So how does that apply to what we are talking about here? What we are talking about here is p is basically saying, let's see, what should I do here? Okay, we are talking about pigeonholes. So we can say at least one pigeonhole has more than one pigeons. So p of x is saying x has more than one pigeons. There we go. Alright, so this is our p of x, which means what we are doing here is not gonna represent the original theorem, because the original theorem is basically saying there exists x such that p of x. Okay, so given P of x is defined as x, which is a pigeonhole, has more than one pigeons, then the original theorem, or is basically saying at least one, okay, and therefore we use the existential quantifier, there exists at least one pigeonhole such that P of x is true. All right, so if you want to be kind of careful, okay, in pigeonholes, there we go. So now we make sure that X is a pigeonhole before we confirm that there are more than one pigeons in that pigeonhole. So now the question is, what if we want to negate it? Because that's the first step of proof by contradiction. So you want to negate it. So by negating the quantified expression, the first thing is you change the existential quantifier into a universal quantifier. So now it becomes for all x in pigeonholes. Okay, but then you negate whatever the predicate is that you have in the original one. So this is the negation. These two are the same. Okay, this expression here is exactly the same thing as this expression over here. So what does that mean, right? What is not P of x? Well, if you just kind of expand what P of x is, x has more than one pigeons. So not of x means x does not have more than one pigeons. So if x does not have more than one pigeons, that means x has at the most one pigeon. So now we can say x has at the most one pigeon. So so this becomes our negated theorem. So the negated theorem says, every pigeonhole has at the most one pigeon. So how does this cause a conflict? How does this cause a contradiction? So if you make this assumption, so now the question is, how many pigeonholes do we have? Well, we know there are m pigeonholes, right? So there are m pigeonholes. And since each pigeonhole can only have at the most one pigeon, so that means the number of pigeons is going to be less than or equal to m. Does that make sense? Okay, so let's check this again, okay? Because the negated theorem states that every pigeonhole has at the most one pigeon. Because for all is basically every. Okay, so if you don't like the the more mathematician term for all, you can just say every. Okay, every x or every pigeonhole has at the most one pigeon. So that means if you add up all the pigeons that are in the pigeonholes, the number of pigeons can be at the most m, right? I hope so. I hope this is the kind of logical conclusion you come to. But this conflicts with the given n being greater than m, because the number of pigeons is represented by the symbol m, n. So using the negated theorem, we arrive at a conclusion that n has to be less than or equal to m. But the given, which is what is in iota, is saying, okay, don't ask me why, but you are told, and this is true, that n being the number of pigeons is greater than m, which is the number of pigeonholes. So these two obviously cannot be true at the same time, which means the conjunction is false. So to make this more formal, now we can say n is less than of m, which is a conclusion based on the negated theorem, and n is greater than m, which is from our iota, is false. So based on the proof by contradiction technique, when whatever is given to be true and the result of the negated theorem, when that conjunction, this conjunction here, okay, whenever this conjunction, okay, I'm going to do something that Randy Schuster does a lot, which is using a pinging thingy to make people kind of focus to that point. So when this conjunction is false, that proves that the theorem is right. Okay, it is a conclusion. It follows. Okay, logically it follows whatever is given to you. So this proves the theorem. The proposed theorem, I should say, this proves the proposed theorem is a theorem, which is not the same thing as saying the proposed theorem is true. Okay, so you have to be very careful because when I can throw any Boolean expression at you, okay, and I want you to prove whether it's a theorem or not. When you prove something being a theorem, all you're trying to say is to say, given whatever is in iota is true, then that statement has to be true. But it's not automatically true. In other words, the theorem here is to say, the theorem here is basically saying there's at least one pigeonhole that has more than one pigeons. Okay, that's what the theorem is saying. But that by itself is not necessarily true. All this is trying to say is to say, if there are more pigeons than there are pigeonholes, then there's at least one pigeonhole having more than one pigeons. So you have to be very careful because there's always an if in this case, okay? Because the left hand side of the implication is what is given to you to be true, which is basically all the elements from the set of iota in propositional logic. And then the theorem basically is a consequence of all of those things. So you have to be careful when you make the conclusion. What we are trying to what have we proven here? All we have proven is the proposed theorem is not just proposed. It is indeed a theorem. It is logically following what is given to you to be true. So that part is kind of important. All right, so I'm looking at the clock here. I have just yacked about for an hour. And normally in a class, I would have, answered questions and, kind of slow down and paused a lot, because, some people are watching it from YouTube and there's a lag time. So I'm thinking in terms of content, this is actually the equivalent content of one lecture, which is 80 minutes. Even though I have only spent about 60 minutes, but I think the density when there are no questions and no interaction with you guys, the density is a whole lot higher compared to when I'm actually teaching in a synchronous mode. So I'm going to stop here, okay, because this is already quite a bit of stuff to absorb, specifically the CNF part, turning a general expression into CNF. So what I'll do is I am going to give you another example, so you can practice, okay? This is not a part of your homework assignment, but you can use it for practice purposes. So let me give you something that is that's going to be a little bit more interesting compared to the one that I showed you. So I'm going to have P implies R, and let me see. Yeah, so we have a and R or P or R, Q or R, Q or not R. Okay, there we go. And then we have a OR here. And let's give this another implication. We'll make this R implies P and Q. There we go. And I think I got one too many parentheses. This one is not needed here. There we go. All right, so this is just for you to practice. Turn this into a CNF. It's just for you to practice. And then on Monday, I'm going to spend some time to explain how to turn this into its own CNF. And And by the way, the homework assignment, for those of you who have kind of clicked on it and see it already, I'm going to change those expressions too. So, those are not going to be the actual expressions for your specific assignment. But this is going to be a practice, okay? Use this as a practice, and then on Monday we'll talk about it. All right, so I am going to stop the recording, upload the video, so that you guys can watch it over the weekend. Thanks.